Welcome to another GCBASIC tutorial for the PIC18FxQ35 chip family. This is part 16. We're going to cover program memory, SAF memory, EEPROM, data blocks, basically storage as I call it. So please like this video and subscribe. So what, as I said, oh, that's not correct, is it? The PowerPoint's not quite right there. The PowerPoint, I'll update the PowerPoint. We're on number 16, not 17. So I will do that live for you. I will quickly change that. There we go. Hold on a second. Get rid of that. Get rid of that. There we go. Change it to PowerPoint live. Using storage, program memory, SAF, EEPROM, and data blocks. Quite important about storing data. So let's get started. I'm using this board. This board is a PICDEM 2 plus demonstration board. Now, the only thing, we're not actually going to, well, we can show the LED. Let's have a look at the camera. Oh, there it is. Look, that's the board. So I've got a Q35 here. Actually, I'm going to put some stuff on the LCD, but to be honest, I've got a better way of doing it. We're going to put it out to the LCD, some information out there, but we're going to put it out to the serial. But this is the board. It's a great board. There is nothing wrong with this board. I've got to be honest. So let's go straight into what we're looking at, storage. Now, I call it storage because I'm a professional, and you could call it memory, but it's not memory. You could call it EEPROM, but no, the higher class is called storage. It's data at rest. And basically, you've got three major types, as I can call it, and you've got Progmem, or program, where you put your program, and you've also got something called storage area flash on this particular chip, or SAF. You've got RAM. Now that's volatile, so you can put variables in there, but when you turn it off, it gets lost. And then you've got something called EEPROM, data EEPROM, and I consider that as a peripheral because it's a different library, different addressing mechanisms, and it's useful. But you can still peel back these three different types even further. Because flash memory, or Progmem as I call it, comes, you can have your program, the blue areas. It's either at the top or bottom of, let me just bring my pen up. It's either here at the, what I call the bottom of memory, or at the top of memory. And depending how your compiler works, it might do a little, essentially the program runs along like this. It runs in this sort of direction. Starts here, and takes the next block and moves along. But in some compilers, it jumps to the first place and then it vectors it out to the program and then runs along here. But you can have your program in there, but you could also put other data in here. You can put reference data, a block of that, and a block of pictures maybe. And for that, you use something called PFM direct addressing, so you can talk to it via some APIs. And you can do the same in the others. Now, let's be quite frank. GCBASIC does it this way. We load it in the bottom of memory. So what you could do is this. You can actually put reference data into the PFM, program flash memory, and you must make sure that you don't overwrite the program. That is the crucial thing. Do not overwrite the program. Bad news. If you've got a bootloader, different issues, but that's the principle of storing information, reference data, in program flash memory or PFM. You've also got something called SAF, and SAF starts at the top, at the point, at the maximum memory point, and comes back an amount. And I think on this chip, that's 1028 bytes. Now, it's word addressable, but if you read the specification extremely carefully, you'll see it's only bytes that are actually safe. And what you do, you have 1,000 bytes, and you can store data in this area here, in where's my pen got? It's red on red, look, in the SAF area here. And therefore, if you have a program that sits at the top of memory, you just need to shuffle it down a bit. And again, if your program is very, very large, you could overwrite this area. There is a risk of that. In GCBASIC, we use what's called SAF offset addressing, and that basically means that the first byte here is address 0 right the way through to the end, and you don't really have to worry about how it all works. So it's really good for storing non-volatile data, and it can be protected because you've got configurations switches where you can stop this from getting overwritten. But you've still got more. You've got EEPROM, EE data, that's EEPROM blocks where you can put byte-only data. But we've also, in GCBASIC, got something called a data block where you just literally have a data block and it just appears in your program. So you've got EE data, and they're two different things. One goes directly into EEPROM, and the other one goes into the top of PFM. Both areas can be used for reference data. There's lots of choices, lots and lots of choices with respect to storage. So I'm not referring to RAM here because RAM's for variables, and that's automatically allocated in GCBASIC. But what we're going to look at is all these different examples in terms of writing to program memory, writing to SAF, and creating EEPROMs and data blocks. Hard to demonstrate all this, but we're going to give it a go because we've got a chip and we've got some serial terminals. We can have a look. So let's go back to GC Studio. GC Studio, open it up. We've seen this many times now. It's doing an update today, is it? Great. There's an update coming through from, here we go. I am going to open my local folder, and that local folder is as follows. I'll zoom in for you. Demo vendor boards, microchip, PIC18F plus board 2010 18F. Click on that and select it, and it will then bring up the IDE. Here we go. We're in the IDE. I'll make it a bit bigger for you. Zoom in, Control plus. Okay, Control B to open up the side window. And we're looking for showing data block. I might rename that actually. Showing storage might be a better name, okay? All right, because ST showing storage to showing storage because it has the LCD on it, but you know what, it's not the only way. Okay, let's get into our program. Control B. The header on this is identical to what we've seen before. Chip specification, option explicit, and I've got the reset button set. In terms of what I've got here, I have got a switch, ADC, some LEDs. I've got a transmit on C.6, LCD, port D, and a reset button on E.3. I've set up the PPS because we're going to be using that for C.6. Not going to go, there's other tutorials. The rest of this is all about setting up the board, and then we get into this particular area here. So the first thing I'm going to do is I'm going to have a swig of coffee. I am going to show you how you can read blocks direct from memory. Direct from the program memory. Program read is essentially going into the PFM, program flash memory, and pulling data out. And it's going to pull it out at some address, which I will pick in a moment, okay, and put it on this. It will put it on the LCD, but it's also going to put it on the terminal. And using the terminal for this is real justification why you want to use a terminal. So I'm going to read some data here, program read, and I could use program write, but let's just do program read to start with. And I've got something that's called my data block. And so it goes, oh, right, that's an address. Program read takes an address, and this is an address calculation as the first parameter, and it's going to put the result in my data word, and then it will put that data word on the screen. And where do I get this data block from? Well, if you want to put reference data in, what was it called? Data block 1. Here's my data block. Now, I have seen programs that are huge for data blocks. I'm just using a few words here, okay? And it says here, I'm going to put some data words in here called 1, 2, 3, 4, 5, 3, 4, 5, 6, 11, 11, 11, 22, 22 hexadecimal values. Put those into memory. Put that lot in memory, into the PFM, because it says data, end data. And this is and there's one above here as well. So we're going to have a look in a minute. We're going to make this get into the program memory. Oh, how does that work? Well, let's just program it. And we're going to look at the program that's in that chip, and we will find exactly this data sitting as reference data in our program. I'm going to start up PIC18FxxQ35. Why? Because it's got a UI in it that I can use. Put it on the screen here. Just zoom in. Oh, that's good. I'm just going to read the program. Then we're going to look at the actual program and have a look for that data. Well, here's the program itself. Look, it's quite large, a load of hexadecimal, as you can see. I just cursor down, and on the top of the program, we've got some reference data, and we're looking for 1, 2, 3, 1, 2, 3, 4, 3, 4, 5, 6. And this is really good, isn't it? Yeah, because that's exactly what's in the data block. 1, 1, 1, 1, 1, and 2, 2, 2, 2, 2, 2. So what happens is if you have a data block, it gets put in, right, it's automatically put inside the PFM. So let's have a look what was displayed on the terminal. Function key F9, open up a terminal. I have a TTL USB converter connected. If I connect to it, press the reset button on that board. And it says here, at address D7C, there was a word found. Now, why is it doing it slowly? Because it's also putting it out to the LCD, and the LCD, you need to have a way of displaying things. So you don't have to have weights with terminals, different issue. So if we look in our program, that is the reference, D7C. Let's go to PIC18FxxQ2. If I hover over here, it should give me the address, D7C, 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 exactly correct. So where did I get that from? You can obtain the data block address, put it on the screen very simply. Is here, all I said was print the, where was it here? Print, here we go. This basically says, tell me what that address, return the address and put it into a hexadecimal string for me. The commercial at means get the address. So what we've seen is that we can write into the PFM reference data as my table here and read it back with ease using program read. Really simple. And I don't have to know where it's stored because I get a reference back via the table name. So this like block of data or table, I just refer to it with the commercial add. So what else was in that program memory? Let's have a look. Zoom in. There's some other data here before it. Look, is there some other data before it? What's this here? Look, this says 1, 2. There's some other data here. What's this data? Well, if we look at our source program, we've got the values 1 through 8 in as bytes. Remember that if you write a byte, it's actually been put as a word, and you just have to be careful about how much, if you want a word, put words in, and you just need to figure out yourself whether you need bytes or words. And in that PIC18F there, we can say the number 1, the number 2, 3, 4, and 5, etc. This is 0, 1, etc. all the way through, like 7 and 8, 5 and 6, 3 and 4, 1 and 2. Now, this code here is actually from the actual program itself. So what else can we do in here? We can write to the SAF in my little program here. Write to the SAF block. Let's just look at what SAF block is first. Here's the chip again, looking at the chip. SAF, I said, lives at the top of memory, which it does. So if I pull down somewhere in this block at the bottom, I'm looking at the bottom of the memory, I've got SAF. If I just check it here, it changes the color. So I can look at the SAF look. Now if I cursor up, I'm going to show you the first byte. Did I read the SAF in? That's the question. So I just reread the chip back in. The reason it didn't work to start with is all these 3-second delay for the LCD. So if we look at the first word in the SAF, it says FF55, and that's exactly what I wrote out. Let's have a look at the source. It says here, SAF write 55 hexadecimal. Let me just show you this look in detail. I'm going to put another one in here and go AA. I'm going to program that, and it's going to take some time to come through, at least 15 seconds to come through because of all the delays in this program, which is disappointing. And what I then do is I put that data out on the terminal. I'm only going to, I'll come back to that second byte we've just put out in a moment. SAF, and it says here, read that back. SAF read and SAF write are the two commands. So if we look here, it says here that SAF address 45? What have I done there? I've done it. There's something wrong there, isn't there? So I was looking at the terminal and something wasn't right. Let's look at the terminal now. If you look at the terminal now, it says here that I wrote out a 55 hexadecimal, and the terminal is now returning 55. I haven't changed the code in the library, sorry. What I did, I was actually incorrectly putting the serial data out. So I've changed to a string, H serial string carriage return line feed. I did not have that previously, and it was giving an errant result because I was actually passing it an ASCII value. So what we got here, a way of writing to the SAF memory, but I put another one out there called AA. So let's have a look what that's done. I read it in, and here it is. It's put it automatically into the correct location. So you don't have to worry about pages and blocks. It's all done for you. Because to write a block, to write a byte to the SAF memory, you have to read the whole block into a cache, change the byte or bytes you want to change, and then write the whole block out. That's done automatically via this SAF write. There are a whole lot of functions called that do it all for you. It's the only way to do it properly. Let's look at other memory. EEPROM. If you want to put reference data directly into the EEPROM, you simply use the EEPROM and EEPROM block. So you give it a parameter, the name of the block, optional location. Here is so therefore that's deferred to 0. EEPROM my data 2, address 16, and some more reference data. Let's have a look what happened in PIC18F, if you can see that. Down here in the EEPROM block, it says 1, 2, 3, 4, 5, which is what was in our data. It was in our data set. And then it says here 5, 4, 3, 2, 1, 0. Oh, sorry, 0. Where did that come from? 5, 4, 3, 2, 1. Let's go back to the program. So we got a count up and a count down. Remember that. And here it is, a count up and a count down. And this is address 16. Is it address 16 in here? Let's have a look. It's at address 16 as 10 hexadecimal, so it's put it in the right place. So what we've got in this one program is reference data in EEPROM, reference data in SAF. We've got reference data sitting at the top of memory here. So we have lots of ways of storing reference data with ease. And I'll show you some tricks. Desktop, I'll show you some tricks. Hopefully this will work. Not really tried this. You can mix and match. Where is that going to put it? Let me see where that goes. F5, function key F5. You can also put in escape codes. So I'll put an escape code in, like a 00 or carriage return, whatever you want to put in there. I'm going to read the memory back in. So I am going to have Evan inside of the EEPROM. You can put text in, you can put all manner of things in there. Do go and have a look at the help on this. Let me just change this to word ASCII, or which one do I want? Word ASCII or byte ASCII? We'll have a look. This I'm looking at the editor EVAN. It's done it. Now it's not the best use of memory because these are word addresses and they're treated as bytes. That's the way life is, okay? If you want to pack it, then do it differently. You've got different ways of putting in strings in here. Please look at the help for what you can actually put in here. It is pretty extensive and has been modified in 2026 to be far better. Okay, where are we? I think we're done. Memories. Let me look at my PIC2. We've looked at PFM. We've looked here. Oh, you can also write into the user IDs, of course. User IDs are up here. There's a user ID block. I'll just bring that. Is that being shown? Let me zoom in on the desktop so you can see it. There's a data block here. You display the user IDs. There's another little data block of, gosh, I don't know how many bytes are in there. Look, how many are in there? Let me just hover. It won't do it. Oh, there you go. How many data bytes? So in here, it's got Progmem of 32K, EEPROM of 256, HEF-SAF for 1024 bytes, and let me have a look. That looks like a lot of config user ID memory. I guess you can change it in here, but you can write from it. Just write your own routine inside of GCBASIC to update that too. With that, I'll give it a break and let you go. Back to PowerPoint. So next, we'll be using CLC. So a lot of what we've been doing, I'm going to replace with CLC, configurable logic blocks. Enjoy.